Welcome to the lab. I'm Mikey, and today we're starting on an awesome project. We're going to be building an 8x8x8 LED matrix. I've wanted to build one of these for a while now. So lab coat up, we're going to learn something today. So what is an 8x8x8 LED cube? Well, technically, it's a 512 pixel, three-dimensional display. They are often used to display impressive 3D animations. Some people have built theirs to be reactive to sound and music as well. But you know our policy. If we're going to build a project that others have built, we need to expand upon it. As such, ours will be internet aware and have Bluetooth connectivity. Why not? We'll use these to set up the cube as an awesome three-dimensional notification system. There are several examples of these around the internet, and I've linked the two that have inspired me most here and here. One of the original cube tutorials is by a user named Char, and I found it on Instructables.com. You can find a link to his build tutorial in the description below. Fair warning, if you don't have confidence in your soldering skills, one of two things will happen here. This is either not the project for you to start with, or you will have a lot of confidence once you are done. Unlike most other cubes I have seen on the internet, ours is not actually going to be controlled by a microcontroller, but by a full ARM processor in the form of a Raspberry Pi Zero W. What is a Raspberry Pi Zero W? Well, in short, it's a single board computer with a single core 1.2 gigahertz ARM processor, 512 megs of RAM, built-in Wi-Fi, built-in Bluetooth, USB and HDMI support. The best part, this small computer is approximately $13 Canadian. For more information on the Raspberry Pi, check out this video here, which is part of our basics series. So let's dig into this project and start planning and putting together a list of parts for the physical build and a preliminary list for electronics, which will probably change and expand as we plan that section of the third video. The first question we need to address is how do we control 512 LEDs individually? And the answer is simple. We don't. We use a visual trick called persistence of vision. Let us take a few moments to discuss the general overview of persistence of vision, and then we will dive down to the desktop and plan out our implementation. Persistence of vision, or POV as I will refer to it from now on, exploits a limitation in the human brain. In the simplest terms, it takes a significant amount of time for our brain to observe change. Much longer than it does for us to light up something else. For example, if we have two LEDs here and here, and we turn one on like this, you can clearly see that one of them is on, and one of them is off. If we turn the one that was on off, and turn the one that was off on, you can observe the change. But what happens if we increase the frequency of that switch, like this? It becomes more and more difficult to detect the switch. At any given time, one single LED was on. But once we reach around 30 Hertz, it will appear to your brain that both LEDs are constantly lit. We are going to take advantage of this concept by scanning through the layers of the cube at a rate high enough to fool your eyes. By doing this, we only have to control about 64 LEDs individually and switch between 8 layers at a rate of 60 Hz or higher. This means we only need 72 I/O pins for the cube. but none of the Raspberry Pi, Arduino, or Pix have 72 I/O pins. So we're going to need to use something, and it's a jelly bean part, in the form of a shift register. As you will see in the control circuit design, I'm using two sets of shift registers. One bank with 64 outputs for the columns, and one with 8 outputs to switch the layers. These will be controlled from the controller with 4 output pins, either via SPI or I2C, depending on how we plan it out. If you don't know what any part of what I just said means, don't worry. We will explain in detail as we proceed through the series. The first decision we need to make before we can build the physical cube is the current flow inside the cube. More precisely, will each layer be common anode or common cathode? And what does that mean? Since we are activating each layer with a single pin and lighting any of the 64 LEDs on that layer with one of the 64 columns, we need to determine if the single connection to select a layer will source current, provide power, or sink current, provide a path to ground. The decision we make here will limit our choices for control of the cube later on. For our particular design, I'm going with common anode, as depicted in this schematic. As you can see, each line common to the plane for all of the LEDs will source current to all of those 64 LEDs. However, the LEDs will not light until the other leg of the LED is connected to ground. So when we want to turn on a specific LED, we supply current to that layer, and we pull the pin for that column to ground. When the LEDs are off, the path to ground for that column is blocked. Or in other words, the pin is left floating. This decision will allow us to use a jelly bean component to control all of these LEDs, and that is the 74HC595 shift registers and the ULN 2803 Darlington transistor array. This video series is going to be broken into 4 parts. This video, the next video, which will be the build steps for the cube itself. This is a very in-depth process, and we will take you through every step. By the end of that video, you will have an assembled cube. To complete this phase will take on average 3 to 5 days, if you choose not to drive yourself insane, since it's a lot of the same action over and over. In this video, we will also present the finalized parts list for the cube itself. And then we move on to part 3, design and build of the control circuitry. In this video, we will finalize how we plan to control the 512 LEDs. We will make more distinct decisions based around the limitations that we set out for ourselves when we initially built the physical cube. I am mostly referring to that common anode versus common cathode for the individual layers. And then we will wrap the series up in part 4. This will be the software. In that section, we will design and implement the software that drives the cube, communicates via Bluetooth and Wi-Fi, parses information from these sources, and from any connected cell phone. This is going to be a very interesting project, so join me at the PC where we look at the parts that make this up, we look at the data sheets for them, and we explain why we chose every single one of those.
Okay, so here we are at Digikey. This is a great supplier for electronics parts. Some of its prices are a little higher than other places, but you always know what you're getting. The selection they have is amazing. The shipping is remarkably fast. And you always know that what you're getting is not a clone. It's not something that fell out of the back of the factory or a B-grade product. One of the other things that I always use this site for is the data sheets are always linked to the product, and the data sheets are always accurate. There will be a There will be a Maker's Basics episode done on reading the data sheets because they can be quite lengthy and can be quite difficult to read. So why don't we just take a moment here and we'll scroll down and we'll look at the basic parameters of this particular product. Now this particular version of this chip, since the 74 Logic series is just kind of made by everyone, is made by Texas Instruments. I'm not exactly sure why, but I always seem to use that one. It is distributed in a tube, and it is currently active. Now this is important mainly if you're looking to build a product where you'll be selling it to other people. Active means that it's currently being produced. Obsolete means that you may be able to get stock now, but the factory is not making any more. So again, if you're going to be doing a product to sell, it might be hard to get to it. This is, of course, a shift register, right? And it's the serial to parallel shift register, which is a 7-4 series logic chip. This, of course, is an 8-bit chip, serial to parallel. And its acceptable voltage range is 2 to 6 volts, which means it should work with 3.3 volt logic. However, we may need a logic level converter for that. The temperature range is obviously irrelevant to us. The type is through-hole, which is great for prototyping with. It works well with breadboards and getting a circuit planned out. However, if you go to produce this on any type of a large scale, on any type of a product that you will be selling, you probably want to switch to an SMD version of this chip. Okay, so this is the data sheet for the 595 shift register. As you may have seen up there when I move the mouse, it's 35 pages long. Everything you could ever want to know about chip is inside this data sheet. As I mentioned before, we will have a beginner series video on how to read these things because it is a little bit of an art. So now we're just going to scroll down a bit here and look for some of the relevant information that we care about. Yes, here's the one of the pieces that we need. This is the pinout, and this is a pinout of the dip package, which is the one we ordered. It's always good to look at these pinouts. A lot of the times they're not as intuitive as one would assume that they would be. You'll notice pin 15 there, right, is the first output, and pin 1 is the second, all the way through pin 7. I don't know why they made the first output to be pin 15, but that's what they did, and that's what we have to work with. If we continue to scroll down in this data sheet, we're going to get a pin description chart right here, which basically tells us exactly what you would think it is. But again, for those who've never worked with the chip before, sometimes it's interesting to look here. As you can see, we have an output enable pin. What this will do is it will allow us to turn off or on the entire output of the chip with a single command. And through here we have the control lines for this chip, which we will definitely go more into detail as to what they are and how they work when we start to lay out the control circuitry. The other thing that we want to look at is the absolute maximums for this particular chip. A lot of times when engineers talk about the ranges or what a chip can handle, there's a safety net built in. This particular table will always tell you what the actual value is with that safety net removed. So for example, this particular chip, it looks like, will take 7 volts. This is a momentary 7 volts. It won't like to take that very long. The other things we definitely want to look at here is the maximum current ratings. So driving wise, the maximum current that it can put out is 20 milliamp. Now originally when I was looking at this, I made the mistake of thinking that with our particular application, that this might be an issue for us because each LED uses 20 milliamps. But then I remembered that we are using the ULN 2803 chip as well, which is a Darlington transistor array, which kind of removes that requirement. The 20 milliamp range will be more than enough to saturate the base of that particular transistor and cause it to close. This here is another piece of the data sheet that will be very important to us later on. We will go more in depth with it when we actually lay out the electronics and when we look at the software, but this is the signaling example chart of how this chip works, what signals it's expecting, and how the behavior will come out the other end. You'll notice that this looks very similar to what we will see with our logic analyzer. So we're moving over now into the ULN 2803 chip here at Digikey. Again, we're probably just going to drop straight to the data sheet since that is generally the more valuable piece of information. Okay, so here we are at the data sheet for the ULN 2803, the Darlington transistor array we were going to be using. One of the things that's interesting about these particular data sheets, if you look, it will give you schematics of all of the individual components that are inside of this integrated circuit. Sometimes this can help to take a look at this and understand what's actually happening in this, we'll call it a black box type of a device. The pin configuration, though, pretty much outlines exactly how this device works. Right, you have your inputs, you have your outputs, and you have your common. So basically, when you take one of the inputs high, it joins the output and the common. So for us, that will be joining an output to a common ground, right, which will allow us to sync current through the chip itself and light up an LED. Okay, so now we're going to look at the actual components for the physical build. The first place we're going to stop is eBay because we're looking at 1,000 3mm blue LEDs here. Some people have built their cubes using 5mm LEDs or 10mm LEDs. You may want to consider adjusting the spacing for your cube if you're going to use LEDs that are that big. I went with the 3mm because I wanted a tight but open kind of feel to the cube. It is also very important that you get the 1,000 pieces. I know we only need 512 for this particular project, but I often find that up to 15% of the bulk products I buy from China suppliers are defective. So this gives us a buffer, and we'll definitely have some extra LEDs, but at 1,000 for $8 US plus free shipping, right, it's definitely worthwhile having them out on hand. We definitely want the super bright version of the LED. We do want to try to make this cube somewhat visible during daylight, and we definitely want diffused. Reason being is that with the diffused, it kind of spreads the light out over the entire dome of the LED. If we zoom in here, I can show you what I mean. On a non-diffused LED, the light is concentrated at this point right here, whereas with the diffused LED, it tends to go over the entire area a little more. So when you're viewing the LED from the side, as you can see here, it's a little more visible out the other sides. Whereas with a standard non-diffused LED, right at the tip here is where all of the light will be concentrated. So unless you're viewing the cube from the top, it's kind of pointless. Alright, so this is what I call silvered copper wire. It's a beadsmith wire, generally used for art and crafts with beads. However, it has an interesting property to it that I like very much for this project. If you take it and you stretch it, it straightens itself out and stays straight. It is a non-tarnishing wire, so it will work well for the structural support and electrical connectivity required for this cube. I'm going to grab 2 rolls of this, simply because I know how big of a cube I'm going to be making. I also just, as a side note, I also use this a lot for laying out PCBs. I don't like doing the drag solder technique on the bottom of proto boards, so I tend to use this to link pieces together. It makes a nice project out the other end. We will do a Maker Basics series on how to use this particular wire because it is incredibly useful. Okay, and the last piece of things we're going to need for the physical build is some foam core board. And to be honest, you can probably better find this at any dollar store near you. You usually get a big sheet for $1 or $2 there. What we're going to use this for is we're going to use this to build our spacing template for LEDs. Right, we're literally going to punch the hole, 3mm holes in one side at a grid spacing of, I believe we're going to probably go 25mm apart from each other in both axes. And that will give us a nice even spacing and make all of our layers identical. Again, you can order this from Amazon. There will be a link in the description below for it and everything else that we've looked at here.
Okay, so to recap, today we took a look at the project, we took a look at the goals, and we took a look at some of the challenges that will come when we try to work through this. We took a look at a couple of the components, specifically the shift register and the Darlington transistor array, which will definitely be part of our final design. We took a look at the 3 products we are going to need in order to start the physical build of the cube. So from here, our next video part will be the actual process of building the physical cube itself. I want to thank you for taking the time to hang out in the lab today. I hope you learned something. If you liked the video, give me a thumbs up. If you have any questions, anything needs to be clarified, or you disagree with anything I said, by all means, YouTube comment section below. Don't forget to subscribe for content updates, and click the little bell icon beside the subscribe to be notified by email of every video I upload.